Daniele Oriti, who will be talking about cosmology as quantum gravity hydrodynamics.
Yeah, thank you. So thanks a lot for the invitation and the opportunity to speak. So the topic of the talk is going to be what happens to space and time in quantum gravity, for the little we know about quantum gravity. And more precisely, how they disappear in many ways and at different levels. And most importantly, how they reappear from the fundamental degrees of freedom of the theory. And in particular, I will focus on the simplest type of spacetimes, that is those describing cosmology, so homogeneous spatial geometries and matter fields. And I will argue that the way we should try to extract cosmology from fundamental quantum gravity models is by interpreting the corresponding regime of the theory as if it was the hydrodynamic regime of the fundamental theory. So first of all, what happens to space and time in quantum gravity? Well, already in general relativity, so this is a sort of the present of space-time before I go towards the future of space-time. So the present of space-time in general relativity is that a lot of the space-time structures we are used to are put into question, and the space-time structures I refer to are the topological manifold, the differential structure, eventual, time foliation vectors, and other similar structures. And the very continuum metric field and other continuum matter or gauge fields, which are the usual tools, the usual dynamical degrees of freedom we use for physics, are challenged. First of all, they're challenged because of different invariance, which says that the dynamics and the generic solutions to these classical dynamics do not have preferred time or space directions. There are an infinity of equally valid local notions of time and space. And manifold points, paths on a manifold, and values of fields at points or on regions are not physical per se. They have to be made physical by defining those physical points and paths through other physical degrees of freedom, through physical reference frames. So when you try to ask, okay, this is the classical theory, what happens in the quantum theory? Well, first of all, you have to tell me what you mean by quantum theory of gravity. And the first simple perspective is that, well, quantum gravity is just a quantum theory of the gravitational field. It's the result of quantizing GR. So from this point of view, you are in the same situation as in classical GR concerning the role and results of diffeomorphism invariance. But to some extent, the notions of space and time disappear even more, because now even the physical degrees of freedom we use to give meaning, give operational physical meaning to points, directions, time evolution, and so on, are of course subject to fluctuations. So geometry will have to fluctuate, the causal structure will fluctuate, any material reference frame will fluctuate, and so on. But I would say that at the conceptual level, this is to some extent more a problem in new foundations of quantum mechanics, because most of what we know about quantum mechanics relies on standard notions of space and time. From the point of view of quantum gravity per se, and is similar, just a bit worse than what happens in GR. And the main reason why it's similar is that the fundamental degrees of freedom are the same as in classical GR. They are continuum fields, which are turned into quantum dynamical entities. And one way to address the problem of constructing physical observables and giving physical meaning to points, space, time, directions, and so on is the relational approach is basically what I outlined. You use physical degrees of freedom to define reference frames, with respect to which you describe the spatial temporal properties of all the other degrees of freedom. This, of course, leaves many open issues, but for me it's an adequate solution to the basic issues concerning space and time in classical GR and in this perspective on quantum gravity as just quantized GR. And I don't remember why I put this picture, it's just nice. The point is that there are several hints that suggest a different perspective. So maybe something more has to happen to space and time in quantum gravity. First of all, there are various results in classical and semi-classical gravitational physics that suggest a more drastic breakdown of the continuum framework and of the whole idea of effective field theory that, on which my previous statements rely. And I don't want to discuss all of them unless you ask, and assuming that I know enough about them to answer your questions. But there are several challenges to the very notion of localization in semi-classical GR, suggesting minimal length scenarios or non-commutative spacetimes, non-commutative features for spacetime. The well-known issue of spacetime singularities in GR also suggests a possible breakdown of continuum itself. The ideas concerning black hole thermodynamics, whose basic logic is simply that black holes are to some extent nothing else than regions in space or particular configurations of space-time. If they have an entropy, they have a microstructure. And if the entropy is finite, then this microstructure is to some extent discrete. And therefore, you're just saying that space-time itself is to some extent discrete. And so, again, a sort of breakdown of the continuum description. And there are others. But the point is that maybe there are underlying degrees of freedom that that build up what we usually call space-time, which is this continuum structure. And the reason for this picture is just the last statement. So this one I remember. This could be just hints, if not for the fact that several quantum gravity approaches are actually discovering this type of non-spatial temporal, at least not in the usual sense, atoms of space, fundamental building blocks, fundamental degrees of freedom constituting space-time, or from which geometry has to emerge. So this gives room to a different viewpoint on quantum gravity, which is that quantum gravity is not about quantizing GR, but is about understanding and controlling this microstructure of space-time. So there are two main goals: to identify what the fundamental degrees of freedom are, the atoms of space, and define a consistent candidate for a quantum dynamics for them, and then show that a continuum in classical space-time and geometry emerge from them in some approximation. In order for the emergent description to be satisfying, it has to contain GR and effective field theory up to whatever modifications are suggested by the theory. So these two views, quantum gravity is a quantum theory of the gravitational field in the standard sense, or quantum gravity is a microscopic theory or non-geometric or pre-geometric quantum degrees of freedom. So a quantum theory of the atoms of space. In the second picture, immediately you start thinking of the gravitational field as the result of the collective dynamics of such microscopic degrees of freedom, and space and time as emergent entities. This is what goes under the name of the problem of the continuum, and it can be broken down into several subproblems that become, technically well defined only within specific approaches. And you have to ask which subset of states in your fundamental theory or configurations admit an approximate description as continuum spacetimes. How is this subset dynamically selected? It's not enough to find them. It is the fundamental dynamics that should tell you that this special subset of configurations is somehow dominant or preferred in some regime. And then you have to extract some emergent effective dynamics for geometric observables in the selected regime. And it's a huge program, of course, and in several approaches there are several partial successes, and I'm going to discuss some of them. But first I want to stress again the type of problem we are facing. Usually we phrase quantum gravity as the one corner, the completion of the Braunstein cube, the cube of theories, of fundamental theories, whose directions are labeled by relativity, gravitational physics, and quantum mechanics. And quantum gravity is the corner where you are forced to take into account all of them. But if what I said is true, so the fundamental degrees of freedom of the universe are of a different type, non-geometric, non-spatial temporal, not directly associated to continuum fields, then we are really dealing with a hypercube. There is an extra direction, and it's the direction where actually most of theoretical physics live. It's just that we don't necessarily talk with them. This is the condensed matter people. I have many friends, but they indeed do not talk much with us, and they are too busy with their money. I guess. I couldn't find another explanation. And the point is that the problem of studying the emergent behavior of, due to the collective dynamics of more and more fundamental degrees of freedom is exactly the problem of condensed matter. They know what the theory is at the fundamental level, what they, naive, think is the fundamental level, just a bunch of atoms with quantum mechanics and electromagnetic interactions. And all the rest that we know comes from there. So it's a huge amount of physics. And it comes from the collective behavior of many degrees of freedom, which are quantum and interacting. And I can give you several examples. What I call the n direction is the direction of more and more degrees of freedom taken into account into your theory. And well, from quantum atomic physics, you can go to the theory of quantum fluids if you keep the quantum nature. If you first take a classical limit, then you have a bunch of balls, or little balls bouncing against each other, just classical mechanics of a few particles. And if you take then the continuum limit, you get hydrodynamics, which is very different in general from the actual theory of quantum fluids. So the two limits do not commute. So it's important to distinguish also in quantum gravity the problem of having some microstructure and taking a classical limit from the problem of extracting emergent continuum physics out of the quantum structure and then take a classical limit. The two directions may not commute. Actually, usually they do not. This was another example. So this was a lip service to philosophers. We shall skip. So the first main point I want to make is that in quantum gravity, it seems that space-time dissolves into pre-geometric non-spatial temporal degrees of freedom. And again, when I say pre-geometric and non-spatial temporal, I don't want to say that in any specific quantum gravity approach, the fundamental degrees of freedom have nothing to do with the gravitational field. And so after all, we got there by whatever rational argument or even precise derivation from GR, from some discretization of GR, and so on. So we have a guidelines for what their interpretation in spatial-temporal terms could be. But if you take them as such, they are not continuum fields, they are not a smooth metric, they are not smooth fields, and so on, so something more has to be done. So in this sense, there is this new direction to explore, the direction in which you control the quantum interactions of more and more such degrees of freedom. And you start asking which of the regime of this fundamental theory does space emerge, does time emerge, and geometry is a valid emergent concept. The second main point that I wanted to emphasize is that for all systems we know, if they are quantum in particular, and certainly if they are interacting, the physics of few degrees of freedom is very, very different from the physics of many degrees of freedom. So it is very naive to expect that moving along this n direction, is going to be simple, and there's nothing new that happens. Whatever we have understood about the nature of the few degrees of freedom we have, like discrete geometries or whatever, is enough to understand what the emergent physics is. Okay, in quantum gravity approaches, we are indeed learning to move along this n direction. Now, let me tell you let me give you some examples of approaches where we find a type of microstructures which are more exotic, even though they come in several ways from GR. So in discrete quantum gravity, by which label I put together both quantum Regge calculus and causal or non-causal dynamical triangulations, the postulate, which comes from just a lattice approach to GR, is that the fundamental degrees of freedom are quantized or simplices, just building blocks, discrete building blocks of an extended space. Now, on the left you have a tetrahedron, just a basic building block of a three-dimensional triangulation. And the other two pictures are just tetrahedra put together to form extended structures of different topology, without boundary, with boundary, and so on. And the theory of quantum gravity is going to be some type of partition function. You give a fundamental dynamics motivated by GR for these building blocks, which means that you are going to have an amplitude that tells you what the possible, you're going to have a set of possible interaction processes of these building blocks, which are triangulations in space-time, made out of having all these gluings of tetrahedra. You can think of these little tetrahedra as particles, and that is going to be useful in a little while. So you consider all possible triangulations that are formed by these objects, and you assign to them some amplitude, some weight that tells you one particular process is more likely than another one. And you sum over it. You sum all these possible configurations. And the point is that in all these approaches, the amplitudes that you associate to a given triangulation, a given discretized space-time, is some form of discretized gravitational path integral. And of course, I'm skipping all the details. I'm not saying anything really technically precise here. So all these approaches all these definitions of fundamental dynamics are inspired by taking continuum general relativity, adapt it, discretize it on a triangulation, and use the corresponding action as a weight. This action is going to be a function of some discrete variables coming from having discretized the gravitational metric field. And you have to sum over all discrete data. And in general, you also sum over all the possible processes, that is the triangulations. So in this picture, I'm putting together the basic idea of quantum Regge calculus. That will be this discretized path integral on a given triangulation. And the main idea of dynamical triangulations, which is that in order to have the full set of degrees of freedom, you really have also to sum over all possible discrete structures. Okay, so in this sense, the basic building blocks, again, are not just some smooth manifold with smooth metric fields, but they're reasonably close to it. But still, you have to do a lot of work to connect a structure like this with smooth metric fields, with smooth GR, and so on. In loop quantum gravity, although again we start reasonably with with trying to quantize GR with canonical methods and so on. The result of just trying to do things properly and without trying to introduce new structures or new degrees of freedom, new symmetries, and so on, is that the quantum states of the gravitational field are associated to discrete structures, graphs, labeled by representations or data from the SU2 rotation group, and initially actually from the Lorentz group. So regardless of how you get there, the basic point is that if you ask the theory what is a typical fundamental configuration of my system, which is supposed to be described in some regime by some smooth geometry and space-time and so on. A typical configuration is going to be some graph associated to some graph on whose links I have put some spin, some representation of SU2. That's the spin network here, as one example. And there is a corresponding dual picture in which to each node of the spin network you associate a fundamental simplex, again like a little cell, and to each link there is like a phase of this cell corresponding to is this picture here. So there is a node with 4 outgoing links around which you can imagine having a little tetrahedron with the 4 links corresponding to the 4 faces of a tetrahedron. So in this theory, in a sense, the fundamental building blocks are like these nodes or these little tetrahedra. Now, of course, an electron is not a spinning point object. So it's not that the fundamental degrees of freedom of the universe are little chunks, flat inside that bump into each other. So this is a graphical representation of the fundamental degrees of freedom of the theory you have there. You don't go with a microscope looking for tetrahedra. You can do it, but it's going to take really, really long, and it's not very useful. So you can interpret these discrete structures as generalized piecewise flat discrete geometries. So very similar to what we have in quantum Raja calculus and dynamical triangulations. And so the main point is that anyway, they are purely combinatorial, algebraic, and there is work to be done to get to something like smooth fields. And the second example there is just a few of these nodes corresponding to a few of the tetrahedra stuck together to form extended structures. And this goes on at the space-time level, so at the dynamical level. These are states, these are like the fundamental building blocks. Their histories, their possible interaction processes are of the same nature, purely combinatorial and corresponding to cellular complexes. So they are called spin foams. And you have the same type of map to piecewise flat discrete geometries of a generalized type. So again, the main message is that even if you try to not introduce anything fancy, somehow when you try to do things properly, well, the world will look fancy anyway at the microscopic level. And a way to organize the same type of data in a more convenient framework, well, and I will show in what sense is more convenient in a while, is the so-called group field theory, formalism. It's just taking the same type of structures and organize them with appropriate changes, of course, in the initial formalism, in the language of a field theory. So whatever I was calling, these little tetrahedras, little chunks, little quanta of your space, well, you treat them as quanta of your space. They define a Fock space, and there is a field theory governing their dynamics. The quanta are exactly these spin network vertices, or quantized simplices. The possible fundamental interaction processes, the Feynman diagrams, are exactly these simplicial lattices, or these spin foams. And the theory is a field theory. There is a field with creation and annihilation operators. There is a corresponding phase space. There is a Fock space for these objects, whose fundamental one-particle Hilbert space is exactly the Hilbert space associated to a single tetrahedron or a single spin network vertex. Again, the details are not so important at this level. It's just that those type of non-spatial temporal, discrete, combinatorial algebraic degrees of freedom are organized as quanta of a field theory. And the theory gives you some, so you have a Fock vacuum where there's nothing. You haven't created anything yet. Then there is a one-particle state, which is just one tetrahedron or one spin network vertex. And there are generic quantum states that include those when you started glue things together, so to form extended triangulations or complicated spin networks. Okay, these are just many body states in this Fock space. Okay, so this is the main message. And the theory comes, of course, different models. So you have to specify microscopic dynamics, and that means specifying an action, a classical action first for the field theory. Then a partition function, then you can expand in Feynman diagrams. And these Feynman diagrams are exactly the simplicial complexes, the triangulations I was talking about a few slides ago. And the Feynman amplitudes that these models associate to the fundamental interaction processes are indeed, depending on the variables you use, written as spin-form models, so the type of dynamical amplitudes for spin networks in loop quantum gravity, and or in different variables, but equivalently, as the simplicial path integrals for gravity, for discretized gravity, that are used in quantum Regge calculus. So the same ideas organized within a field theory. That's the only message. Okay, this is what I said. This is the best picture I could find between 11 and 12 at night for a triangulation. And here is, I'm stressing that it's the basic idea of dynamical triangulations, of summing over all possible discrete structures, with the main idea of quantum Regge calculus, of weighting these discrete structures by some form of discretized path integral. Okay, and this is the same, new side of the Bronstein hypercube from the point of view of spin networks simplices. You can start from a theory with, from a configuration with very few quantum gravity degrees of freedom, some simple spin networks or simple superpositions or spin networks. And you can immediately take a classical limit. The corresponding theory is going to be a classical theory of discrete structures, tetrahedra and so on. Or you can try to take a continuum limit, studying the interactions and the collective dynamics of more and more of such spin networks. And as I said, full quantum gravity is up there. That's where you would like to get. General relativity is supposed to be some classical approximation, so a sector of that theory. But remember that the two directions in general do not commute. So it's not obvious that you can try to take a simpler route. Anyway, whatever works, you try. But one has to keep in mind the distinction between the two directions. Okay, so the same questions I mentioned about the problem of the continuum in general are, of course, faced by all these approaches. The first aspect is to find an approximation of the microscopic building blocks to give an effective continuum description, and there's many results in all this formalism. And again, this is the same type of problem as in condensed matter, to extract effective configurations, coarse-grained configurations from atomic physics, with the main differences which are fundamental is that our fundamental theory does not live in space-time. It doesn't deal with space-time fields, and that means that most of the techniques in condensed matter have to be adapted, at least, or reinterpreted. Moreover, because we cannot rely at this fundamental level on manifolds, points, foliation vector fields, none of those structures, then both the fundamental dynamics and any effective dynamics will have to be formulated in terms of relational observables. It's a bit like the theory by sheer luck gave us directly the deparametrized form of GR with matter fields. It only gave us the relation between physical degrees of freedom, and we had to extract from them relational observables in the continuum. Okay, the second aspect is to actually tackle the dynamics, and that's basically doing renormalization group analysis, extracting possible phases, macroscopic phases of the microscopic dynamics. And again, there are several results in various approaches. And the main question is not only does a geometric phase exist in the continuum, but is it the only one? And if not, what are the other ones? And how can you actually go from a non-geometric phase to a geometric phase in the continuum? Usually there's a lot of physics in phase transitions. Okay. Oh, this is just molecules forming through a phase transition, condensing to a fluid. In a similar vein, we are inspired to think of these little tetrahedra, or these little building blocks condensing in a way to form some smooth but maybe still quantum and fluctuating space-time. Again, I'm pointing out that in the continuum, the space-time we get may still be quantum, still with fluctuations on, because in what I said, I didn't mention yet the classical limit. I only mentioned the continuum limit. Okay, and then you can even go a little bit farther in trying to understand what these different phase structures could be. Well, first of all, if this is the phase diagram of quantum gravity coming from the fundamental theory, it could be beyond the range of effective field theory, including asymptotic safety. So if you start from continuum GR and try to draw the full phase diagram, you just may not have the right tools. This could be instead, if, for example, the non-geometric phases are described at some effective level as sort of fully degenerate from the point of view of the space-time geometry, like zero expectation value of any metric observable, then this is sort of a realization of the idea of the gravitational Higgs phenomenon. It's sort of like, symmetry breaking from a fully different invariant phase, but it's also fully degenerate, to one that is close to some effective geometry that by definition is going to break different invariants spontaneously. And another suggestion, just at the level of suggestions, that the transition between a non-geometric and a geometric phase could have an interpretation in cosmological terms as what replaces the Big Bang, the classical singularity of continuum GR. So this could also relate to what Robert was saying about emergent universe. From the more fundamental quantum gravity point of view, what he was calling the emergent phase, or the previous phase before the standard cosmology phase, is exactly one of these non-geometric ones. And the transition that gives rise to standard cosmology is this geometric phase transition. Okay, it doesn't mean that it's incompatible with bouncing scenarios, but they could be true at different levels of description. And we like to call this geometrogenesis. I mean, some people introduced it some time ago, and it's super cool. And so we call it like that, the generation of geometry out of non-geometry. Okay, and I will talk about, this is another nice picture. I will give you an example later of a framework in which this is being realized, at least as an attempt. Okay, now I will focus on the problem of extracting continuum physics from the fundamental framework. In particular, I will ask myself, and I will ask you to ask yourself, what is cosmology from the point of view of this fundamental description not based on space-time degrees of freedom and smooth fields. So there's no general answer. There's no obvious signature of this class of models, formalism that I can offer you as, if any of these general ideas are true, this is the signature. It's very much context dependent. So I will give you one particular realization. One thing that should be clear, and that's the other main message, is that if this general scenario is true, although I cannot offer specific proposals for general or generic observational signatures, what should be clear is that none of the usual ingredients of effective field theory can be taken for granted. Not locality, not unitarity. Well, locality, because if at the fundamental level there's just no space-time, well, your notion of locality is part of your definition of a smooth description, and clearly is emergent as well. Unitarity will usually refer to some time evolution, and I told you that at the fundamental level there's no obvious notion of time, so you have to have some refined notion of what you mean by unitary evolution. Space-time symmetries, local or global, also, you shouldn't take them for granted. The very notion of separation of scales, scale respect to which metric, which geometry. The topology is going to be emergent. I told you that the fog vacuum in group field theory, for example, has just no structure whatsoever. The fact that configurations have a given topology or another one is part of what the dynamics should tell you. And so on. So you should expect both modification, concerning cosmology, you should expect both modifications of the background cosmological dynamics, like a bounce or some large-scale acceleration and so on, and then modifications of the effective field theory for whatever perturbations you have. Okay, then I ask the more specific question, what could cosmology be from the point of view of quantum gravity? Am I half time?
Yes, we started about 11, 10%.
Okay. So let's ask what cosmology should be from this point of view. The first, the simplistic sort of definition would be that homogeneous geometries are just special configurations of the gravitational field, and cosmology is the dynamics of such special configurations of general relativity. So just cosmology is the homogeneous sector of GR, the simplest type of cosmology. So there you have a small number of observables, and they're all of global nature. You don't see the local structure, you're dealing with homogeneous spaces. And if you want to go beyond this description in GR, you do quantum cosmology. You take those spatial configurations, you quantize. And if you also have isotropy, then the only variable you can have is the volume of the universe. There's nothing else. And then if you added the scalar field, then you have some homogeneous scalar fields. Your states are going to be functionals of this volume and homogeneous scalar field variables. And your theory will give you a quantum dynamics for them in the form of an operator constraint acting on these wave functions, or in some path integral language. But this is the simplest form of going beyond cosmology, if cosmology just the dynamics of homogeneous geometries, a subsector of GR that you can quantize. So there's a lot of beautiful work on quantum cosmology, and including possible predictions. So it's a very interesting subject. And the difficult problem is exactly what type of approximation does it correspond to from within the full theory? How can it be embedded and realized in the full theory? But I want to say that there is another point of view in which you focus not so much on the configurations of the theory describing the observables you associate with homogeneous cosmologies, but you focus on the observables. So if cosmology is the effective dynamics of spatial, meaning global, observables of the full theory, then cosmology as a theory is the result of coarse-graining the degrees of freedom of the fundamental theory that include inhomogeneities, any local information, and so on, up to global quantities. If you have a picture of quantum gravity that is of the type I tried to argue for, which is quantum gravity not just as a quantization of GR, but as a theory of the microscopic structure of space-time, then the second view of cosmology is a necessity. Because just like any space-time is going to emerge from more fundamental degrees of freedom, in particular, those governing simple observables like the global volume and so on will have to emerge in a similar way. So let me focus more on this second point of view. So what are homogeneous cosmologies? Well, what do? You focus on few macroscopic observables of a global nature. And these have to be understood as suitably defined averages over the fundamental degrees of freedom. You expect it to be valid if you're reasonably close to equilibrium. If the microscopic degrees of freedom go wild, well, you don't expect that these are good observables. So you have to be reasonably close to equilibrium from the point of view of the full theory. And you have to be insensitive, or at least not too much dependent on the microstructure in describing at this effective level these global observables. If this is what homogeneous cosmology is about, then you can think, okay, but if I am near homogeneous, it just means that you're considering a few more observables, enough to have some notion of local structure, the cosmological perturbations, for example, but you're still close to equilibrium and still rather independent of microscopic details up to a point. Then when you go really beyond the homogeneous sector, then you have enough observables to really reconstruct local effective field theory full-blown and GR, and then you start questioning whether it's still valid to think that you are close to equilibrium. and questioning especially how insensitive you can expect to be to the microstructure. But let's focus on the simplest case. And the point is that these basic features are basically the features defining hydrodynamics in if you have a theory, a many-body system. And the other two, depending on what the answers to the last questions are, will tell you whether actually all of space-time physics, including GR and effective field theory, are part of quantum gravity hydrodynamics or not, or somewhere in between the full theory and the hydrodynamics. So let me have a short digression reminding you, or reminding myself to start with, about the hydrodynamics in many-body systems. And again, I want to make only a few basic points. You know the hydrodynamics equations. And the main point is that, again, you're close to equilibrium. The equilibrium will be governed just by thermodynamics. Just very, the full, numbers that you compute out of summing over all the microscopic degrees of freedom and their relations. If you're close to equilibrium, there is still something to do. There is some dynamics. But you're capturing in a small number of macroscopic observables corresponding to averages over microscopic degrees of freedom, the effective physics of a large number of actual degrees of freedom. And key variables are, for example, densities of conserved quantities, which are protected by symmetries, or any order parameter, any quantity that results from broken symmetries. These are usually, stable enough to govern the macroscopic behavior, because exactly because they're sort of insensitive to the microstructure. So for simple fluids, okay, you know what the equations are. And the main thing I want to say is that if you're interested only in a few key macroscopic observables, which are averages over microscopic details, you need to work at the dynamical level just with some key reduced densities. You don't need all the atomic structure. For example, if you have an Hamiltonian for a many-body system, that would be impossible to solve for generic configurations at the microscopic level. Well, but you're interested only in the average of it, which is the internal energy. In practice, your dynamical variables are just the one particle reduced density and the two particle reduced density. So this already tells you that if this is the type of observables you're interested in, global macroscopic hydrodynamic observables, then you need to coarse-grain reduce the information from the full theory to a few key quantities. And again, if you take a simple system of n particles on the real line, then, for example, for all the one-body observables, those that are just the sum of contribution from each particle independently, do not know about the interactions, then only reduce one-body density matters. And you compute it, if you were God, you would compute it by knowing exactly the microstate of all the particles and integrating away all the information about n-1 particles, and you're left with a statistical distribution over the configuration of one particle. And that is the density in phase space, from which you can compute the actual density in space of the many-body system by further integration. Okay, and this is exactly the variable, the macroscopic variable that enters hydrodynamics, starting from the full theory. Obviously, you don't know, usually you need a lot of information to know the microstate exactly, and it's impossible to actually compute the full integral, so you need a lot of dirty tricks and approximations and assumptions, but that's the strategy. And the same can be extended, of course, at the quantum level. One case in which everything is much simpler is condensates. Especially when they are weakly interacting, when you are able to do further approximations. I give you just as an example. There you have a fundamental theory which is bosonic atoms, and you have your scalar field theory describing the atoms, the action there. And what happens in a certain regime of the theory, in the continuum limit, is that the atoms condense. They go into a very special macroscopic configuration. And if you're at low temperature, weak interaction, constant pressure, blah, 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 there is this condensate state, which is an approximate vacuum state. Of course, it's not a solution of the full theory. It's just an approximate description of the true vacuum state of the theory. And this is a very simple state. If you look at it, it's just a linear superposition of states in which all the atoms are in the same quantum state. They all have the same wave function. Depending on the system, could be even a very simple wave function like constant. Okay, so this is would be a simple answers for the microscopic theory, for the microscopic state of your many atoms in the particular regime corresponding to a condensate. It's a particular phase of the full system in a particular approximation. But from this you extract immediately the hydrodynamics, and the hydrodynamic equation is the one I wrote there on the top, is the Gross-Pitesky hydrodynamics. And you can turn into a standard form of density and velocity by just re-expressing the effective field phi 0 as a density and a phase from which you compute the velocity. So just to give it a standard hydrodynamic form. The point is that you have a full knowledge in some approximation of the microscopic theory. You know that the system is in such a state, approximately. This is governed by one function, which is like a one-body function, a one-body wave function, and that gives you your density for the whole fluid. And here we're talking about the description of a large number of atoms in a special configuration, in a special regime. But it's a system with a, not infinite, but very, very large number of degrees of freedom governed, whose dynamics is governed by one function, rho of x, which is in turn the condensate wave function. Okay. So this is just to show that this extraction of hydrodynamics in some cases is more straightforward than in others. So suppose that I want to do the same thing in quantum gravity. I'm interested in extracting effective continuum physics, in particular cosmology, and I trust this general idea that cosmology should correspond to the hydrodynamic regime of the full theory. So what would I do? What I should expect to obtain by some appropriate procedure? Well, the relevant hydrodynamic observables should be, as I said, averages of one-body observables, for example, which are extensive in the number of atoms of space. For example, if the total volume of space would be one such hydrodynamic observable, if indeed the atoms of space each give a little contribution to the total volume. So if you think in a very intuitive way of the whole of space made out of atoms of space and the volume attribution to the full system is the result of little attribution from each of them, then the total volume would be exactly one hydrodynamic observable, one of the simple ones. And another key hydrodynamic quantity, how would it look like? It should be this type of reduced one-body density with a single body corresponding to the atom of space, the individual atom. So tell me, give me your quantum theory of gravity, tell me what it suggests as the atom of space, and I know roughly what type of observables it can correspond to and what the reduced density could look like. So this reduced one-body density will be a function on the space of data associated to a single atom of space, in full analogy with what I said about hydrodynamics. Let me try to be slightly more concrete at the super heuristic level, because none of this formula is well defined. So suppose that you take the basic classical system for which you want to reconstruct the hydrodynamics to be the phase space of GR. So very, very naive. I just know GR, that's my phase space, and I treat it conceptually as if it was a many-body system, with the individual bodies, the individual atoms being just the points in space. Okay? So that's an infinity. It's even worse than infinity. It's a continuity of atoms. But then, an exact classical probability density would be some function on this phase space, the full thing. How would the reduced one-body density look like? Well, I would take this exact knowledge of the microscopic state, this d sigma there, function of all the data, the phase space data of space, and integrate over all the points except one. I'm treating the points as if they were my constituents. Well, at the end, I would get some one-body density, this rho function of the data, intrinsic geometry and extrinsic curvature at one point. But if you think about it, so first of all, which point I take is irrelevant because of diff invariance. Well, this one particle reduced density looks tremendously like, a sort of, so it's a function on mini superspace. It's a function on the space of geometries at a point which is the same as the space of homogeneous geometries. This is classical. If I was to go at the quantum level, I could only use either one set of variables or the other, or some mixture. So it would look dangerously like a wave function of quantum cosmology. But it would not be a wave function in the usual sense. It's the reduced one-body density of the full theory. And what type of equation will it satisfy if this is the basic object? Well, I expect it to be hydrodynamics, so it's a nonlinear equation and nonlinear dynamics for such function. And for the geometric quantities that I compute out of it, like the total volume, which I argued is one intuitively useful observable for this hydrodynamic regime. So you expect that the hydrodynamics of quantum gravity, just on these general grounds, to be some sort of nonlinear extension of quantum cosmology with the same type of basic variable at density on mini superspace, but with a statistical interpretation, just like the fluid density in a fluid, not with a wave function interpretation, not a typical wave function interpretation, satisfying a nonlinear equation. And that already tells you that it cannot be a usual wave function. There's no superposition principle for solutions of hydrodynamics. There's no Hilbert space structure, and so on. Of course, to make this better defined, apart from many, many hours of work and calculations, you need a better theory. So you need some well-defined notion of what you mean by atom of space. But the point is, I just told you that the various approaches to quantum gravity that I mentioned come with a proposal for what the atoms of space could be. So they suggest that an atom of space is a quantized simplex, a little tetrahedron quantized, or a spin network vertex. So at least in these approaches, there is a proposal. They also provide many body observables, volume operators that are extensive in the number of atoms. The total volume of the universe in these approaches is the sum of little volume contributions from each of the atoms. And they also propose a fundamental dynamics for such atoms. And that means that they give you the tools to compute averages, exactly what you need to do hydrodynamics. In particular, in the group field theory framework, all these steps are likely to be more straightforward because you can really proceed in analogy with the quantum field theories of a many-body system, because that's the language. You have a Fock space description for the atoms of space, you have a second quantized language for observables, and you have a field theoretic description of the dynamics, suitable for many-body physics. In fact, I would say that from this point of view, you would have led to invent group field theory, just like in condensed matter or in atomic physics, they started introducing field theoretic methods exactly to deal with many-body systems in an effective way. So what do you expect? You expect the key variable to be a density over the space of data for a single simplex, or over the space of data for a single spin network vertex. And you expect, and then the point that you can show, this is independent of all this hydrodynamic business, that the space of geometries for a single tetrahedron is not exactly equal, but very close to the mini superspace of homogeneous geometries as a manifold, as a space. So really, if you have a density functional over the space of data of a tetrahedron, it would really look like density over mini superspace, as I was suggesting earlier. And you expect, as I said, that the theory should give you a nonlinear equation for such hydrodynamic density. So a nonlinear extension of quantum cosmology. So this is general expectations. Of course, you obtain the general expectations after you got an example. It's not what the textbooks say when you study physics, but it's never the case that you really first have you understood the basic ideas, you have a general plan, and then you realize it in one example. you end up doing things for a bunch of ill-posed criteria and ideas and hopes and so on, or maybe for a totally different motivation. Then you look at the results you got in one particular example, in one particular framework, and say, okay, I should have expected that. This is a realization of a more general picture. The more specific picture is, and then I will conclude in the last 5 minutes. Yeah, 5 minutes. With one realization of this idea, which is some recent work in which we realized this cosmology as hydrodynamics or quantum gravity by studying condensate states in group field theory. That's why I also emphasize that condensates are the simplest framework where you can extract hydrodynamics from the atomic physics. And we are able to reinterpret the resulting effective dynamics, the hydrodynamics of the theory, in cosmological terms, with some interesting results. So this is all really from the frontier. That means that there are many things that we don't know, and I will be happy to answer I don't know whenever you have a question. Okay, so let me recapitulate again the framework. You have a Fock space, that's your type of fundamental degrees of freedom, whose particles describe little tetrahedra. Well, little, they could be huge, but they are tetrahedra. They are expected to be little if you have to put them, many of them to build a finite size universe. Okay, that's I told you that you can equivalently describe this in terms of spin networks, but for now this is not important. And I emphasize again that a generic quantum state in this space will have no spatial temporal interpretation, beside the fact that you are little discrete geometries. In this sense, okay, you can think of geometry, but no interpretation in terms of continuum space-time fields. Moreover, at no point in the definition of the theory, which is the one I just gave, there is a notion of a space-time manifold, of points, coordinates, time foliation fields, diffeomorphisms, and so on. So the first problem is to identify quantum states that admit a sort of approximate continuum interpretation. And we look at quantum condensates as continuum homogeneous spaces. Why? Well, again, of course, there is a lot of information that you would like in a full geometry to have that instead this type of states are missing, but they have enough information to describe an homogeneous geometry, which in many ways is ultra-local. It only knows about the values of fields at a point, and then assumes that they are the same everywhere. So this idea is exactly what is realized even in the simplest condensate, which is a coherent state of the field, which is exactly the type I showed in the Gross-Pitesky hydrodynamics. You have superpositions of many bodies. They are all in the same wave function, and you neglect the correlations. It's a product wave function for each individual element in the sum. Okay, so it's, you have n tetrahedra at in each term of the superposition, each with the same wave function sigma. And you know already that that is going to become the wave function of the full condensate. So you have one function over the space of data for a single tetrahedron describing the whole universe. You're missing, of course, correlations. And you expect correlations to be crucial for many reasons. So certainly you don't expect this to be a realistic model, but certainly correlations are needed in order to know how different points are related. So they may be crucial for inhomogeneities and this type of the spatial derivatives. But as far as homogeneous configurations are concerned, this has enough information. If it has the right dynamics, is exactly what you try to find out. Okay, so this is why you interpret them as homogeneous geometries. And it's based on the fact that I stress again that the space of geometries for a single tetrahedron is isomorphic to mini-superspace, to the space of homogeneous geometries. If you have some additional conditions, which is exactly this type of conditions there. Okay, I don't want to enter into the details unless you ask. So there is a single collective wave function describing what is an infinity of degrees of freedom. Then the second problem is to extract an effective dynamics out of them. But this is the simplest condensate, and what you extract is the Gross-Pitaevsky hydrodynamics, which is in practice nothing else than the classical equations of motion of the corresponding of the field theory for the atoms. So the initial group field theory action you chose give you an equation of motion, and that's directly the hydrodynamics. And you see that if sigma is if the wave function, the condensate wave function, is interpreted as the cosmological wave function, as if it was quantum cosmology, well, then you're going to get a nonlinear equation for that. That's again is the Gross-Pitaevsky hydrodynamics is a nonlinear equation for the condensate wave function. Okay, but I emphasize that it's different from quantum cosmology at various levels. And the interpretation of that will also require a lot of thinking. Anyway, so we solved, this is the solution to this second general problem, which is, what is the effective dynamics for those configurations for which you have a good space-time interpretation. Okay, and this is a realization of cosmology coming out as the hydrodynamics of the fundamental theory. Now, if I have 1 minute to spare, then I tell you that the effective dynamics could actually be very interesting. It depends then on the details of the microscopic model you put in, exactly because there is this direct correspondence between the effective hydrodynamics and the microscopic theory. The Gross-Pitaevsky hydrodynamics is more sensitive than generic hydrodynamics to the microscopic details. So tell me what is your group field theory or loop quantum gravity or spin foam dynamics, and I tell you what is the emergent hydrodynamics. So we did some work recently in which we start with the currently favored spin foam model, dynamics for loop quantum gravity states, which is the so-called EPRL model. And we coupled it to a scalar field, to a free massless scalar field that you have in the same sense in which you quantize GR by going to it, you quantize a scalar field, and so there is some extra variable. So instead of just a GFT field, you have a GFT field depending also on an additional variable, which is a real number. And it's basically the degrees of freedom that should form a smooth scalar field in the appropriate regime. But then you construct the whole condensate states and the effective condensate dynamics the same way. I only emphasize that, again, there's no manifold, there's no fields at the fundamental level. You want to extract a field theoretic or geometric description. And we want to use this scalar field as a clock. Exactly because the only thing we can extract is relational observables. Otherwise, we cannot rely on coordinates or points in a manifold and so on. So then we reduce the system further to isotropic configuration. Up to now, I only mention homogeneity that is captured by this condensate hypothesis. But you can reduce further the dependence to what is basically isotropic configurations. And in practice, you deal with a very, very simple condensate wave function, which is a function of a single spin, half integer number, and the real number that was your scalar field. This is the emergent hydrodynamic equation, some nonlinear equation for the density I've done. You can write it in a more hydrodynamic form if you want, and derivatives are with respect to the scalar field. So in this sense, you are using it as a clock. And then you ask what is the evolution of observables in terms of this clock. So you construct relational observables, which are these one-body operators. This is the volume of the universe for given value of the clock. Then there is the density, the momentum of the scalar field for given value of the scalar field itself. The energy density of the scalar field for given value of the scalar field. These are the basic observables you need to have homogeneous cosmology. And then you use the original theory to compute an equation, an evolution equation for these observables. And you ask, does it look like cosmology? So you ask, what is the evolution of the volume as a function of the scalar field, with source being the energy density of the scalar field itself? Well, you get a couple of complicated equations. But first of all, you can show that, so there are equations for the volume as it evolves with respect to the scalar field. Again, details don't matter, but there are two main features that I want to mention. The second one is that is the one that reassures you. In the classical limit, you get Friedman under some constraints on the microscopic parameters. And this is not strange. I mean, you don't expect that in any regime of the microscopic theory you get GR. So it's normal that the extraction of effective physics gives constraints on what the fundamental parameters have to be. So this is what the theory gives. So you get an emergent Friedman dynamics for the volume, and that's the only observable you're looking at so far, which is good. It's a GR in this very, very special corner. And then you can also show that the volume remains positive at all times. It means that it generically bounds. It never goes to 0. And it has a single turning point, by the way. In this, for deriving these equations, I have assumed that the interactions of the fundamental theory are subdominant. So they are there, but they give corrections to these equations. So this is a strong assumption. But we know that the Gross-Pitesky approximation is especially good for weak interactions between the atoms. You don't necessarily expect it to be true more generally. Okay, and then if you go to an even simpler wave function, a SAP case, then you find an emergent dynamics, which is up to this term exactly the loop quantum cosmology effective dynamics, which is reassuring. So I conclude. I gave you an example that realizes tentatively at least the general framework I mentioned, so it seems to support it. You start from a theory based on non-spatio-temporal atoms of space. So you expect space-time and geometry interpretation to be only approximate and valid for special configurations in some regime. It realizes the idea of cosmology as the hydrodynamics of these fundamental degrees of freedom. It also suggests that the underlying mechanism in the full theory should be some type of phase transition, because I consider condensates, so it's not a generic phase, it's a very special one. And I showed you that, at least in this example, it does give a modified effective cosmological dynamics, which is interesting, not only because it gives Friedman in some regime, but also because it has a bounce. So there is some bouncing scenario there. And of course, there are questions concerning the detailed resolution of the singularity and the theory of cosmological perturbations. But that will be for another day. Thank you.
Okay, so we can have a few questions directly for Danielle, and then we'll switch into the more general panel discussion. So I'll again use my position as chair. I wanted to ask a little bit more about why the focus on the condensate dynamics in particular. So this was partly motivated by the idea that you have this sort of phase transition. Mm-hmm. But it wasn't clear to me. I mean, is there a mixture of motivations here? One might be just that it's a mathematically tractable regime in which you
So in fact, I gave two motivations. So one is that if you're interested in these general scenarios of phase transitions, which we are interested in also the mathematical level when we study randomization group flow of these models and so on, we try to see what type of phases you get. There are some hints that there is a condensate phase. And more generally, it would be a simple phase to realize because it's just determined by the expectation value of the field operator. So you're prompt to look for condensate configurations. And the other one is the other motivation I gave is really practical. I mean, if really cosmology comes from the hydrodynamics of the full quantum gravity theory, the simplest way, the simplest situation in which you can extract the hydrodynamics is for condensate states.
Right.
And so you check that at least as a template of what you're supposed to do more generally. But then we are interested in what could be the more general hydrodynamics of these degrees of freedom.
So it isn't that there isn't a strong motivation of the form. You would expect the state to be a condensate state, and therefore the most natural. Well,
anything that has a non-zero expectation value would be a condensate state. They're not necessarily going to be of that simple form.
Right.
Actually, you don't expect them to be of that simple form. But in any condensed matter system, you don't. This quantum interacting, you don't expect the true vacuum of the theory to be just an exact condensate of an infinity of atoms, all with the same wave function and non-correlated.
Right.
I mean, they interact, so they are going to be correlated.
Right.
So these specific states is just the simplest one you can try. In fact, we constructed more general ones, but it's difficult then to extract the effective dynamics for more complicated states, so it takes some more work.
Right. Yes, Nick?
in the bit towards the end where you coupled it to a scalar field, where's the scalar field come from? Is that in the group field theory, or is that something?
Yeah, so in the same sense in which, where it comes from, so I can tell you where it is, and then I tell you where it comes from. So where it is that in the very definition of the microscopic model, you have a GFT field, which is a function on a certain domain. Now, usually it's the group domain, so it's several copies of a group manifold. Now you extend the domain to include also the real line, so a variable that takes real values. This is what you interpret as a scalar field. So this is where it is. Where it comes from, well, in the same way in which the group variables are interpreted as discretized geometries of discrete data for a discrete tetrahedron, you can show that this real variable enters like a discretized scalar field at the discrete gravity level. So the amplitudes of this model, instead of being just discrete path integrals for gravity, are like discrete path integrals for gravity coupled to a massless scalar field. So it's motivated on equal footing as the interpretation of the group variables.
Would you still think of it as a field in the sort of non-spatio-temporal phase?
Well, in the same sense in which the data associated to a tetrahedron for generic configuration do not build together to form any smooth geometry, this generically is not going to build a smooth scalar field. So in this sense.
Francesca has a point exactly on
It's a
this.
follow-up.
Yeah.
In the sense that you were saying the scalar field is massless scalar field, and coupling a master is very useful in cosmology, for instance, and so on.
Sure.
So have you tried?
Yeah, but then you cannot use it as a clock.
Okay.
So yes, you can. I mean, in fact, we have a general coupling that is much more general than this within an arbitrary potential. And we even tried non-minimal coupling, which is instead a mess, and we don't know how to do it. But so the problem is not to generalize. The point is that if you do that, then you cannot use it as a clock, and I don't really know what the observables should be.
Not even on a finite domain?
Yeah, but you are not in the smooth context. So what you mean by a finite, yeah, in general, yes, you expect that there will be regimes in which you can still use it. What would be more interesting is to couple this massless scalar field and an additional, massive field, because then you check exactly what one you use it as a clock, and the rest you use it as a model for matter.
Okay, so I'd like to thank Danielle. And,